but I think managed to answer your questions online, if there are any.
Okay.
How is it going with the assignments?
So for me personally, I've started to do the AI training model.
Okay.
Yeah, I started to do it, but I think I've hit a roadblock for the coding part of it. So there was a part where you had to go to a website and sort of copy paste a code so that it works. But I don't know. There's like I still have to do it properly. I still have to do
Yes.
it properly. And from that tutorial, what I understood was I'll get the final result that I'll get out of that analysis, that AI analysis, is that I'll get an Excel sheet, but I don't know how that would help me. Like, I thought it would be a more visual output, but I don't think it is.
Both. You will get
Okay.
both the visual output with the boxes around the trees that were recognized,
Yes.
but also an
Okay.
Excel. And this Excel will tell you the amount of trees
Okay.
visible. So you don't have to count the boxes. You can also get it in a table.
Okay. And also when I'm doing this analysis, so for example, in my case, I earlier thought of taking a street in my own country, but I don't think there's a lot of Google Street Maps imagery available there. So which is why I took something in Neder-over-Heembeek in Brussels.
Okay.
So shall I only stick to one street? Because right now during my analysis, I just stick to one street and then took images from that road. That's it, to sort of calculate.
Yeah. In an ideal world, you would have many more training data. Because if you only take it from one street, your model will be very good in detecting maybe this one species that is present in the street.
Yeah, correct.
Yeah,
Yeah.
assume it's an acacia or a pseudo species. It will be very good in detecting that. But if you train it or if you would test it on an oak tree, maybe it will miss it. So it's best to make it as diverse, as representative for the full population of trees. So also take other streets.
Okay.
But of course, it should be manageable. If we tell, for example, base the training on only 20 images, it's impossible to cope with or to deal with the large variety which is there. But it can still be good to zoom out a bit, take some street view imagery from other neighborhoods.
Okay. Around it, yeah.
And it's nice that you go for the more challenging option.
Yeah, just to try
with
it
this
out.
AI or because the view shed, it's also something which can be done if this AI model doesn't work. But it should work. I tested it yesterday again on the car data set. If maybe you can share your screen to
Okay.
so we can look at the error if you would have it.
Okay, I'm just seeing how to do that.
Yeah, I think I should. Oh no.
Got it. Share content and then.
Yeah, I just made you a presenter, so.
Okay, I will just open.
I will make all of you presenters. Yeah. So if anything needs to be shared, we can do this.
Okay, is my screen visible? Oh, okay. I just open that.
Yes, it is.
Yeah.
Yeah.
But currently, so I've created, what I've done right now is instead of starting off with the car data sets itself, I immediately tried with the trees itself.
Yes.
And so I've created these zipped files. I've created, so in the test data images, in the test data set, I have 5 images. And in the training data set, I have, again, I've created, as per the tutorial, I've created images, labels, created those subfolders. But But in this case, like as you see in these images, in some images the trees are starting to blend together. So which is why I'm finding it difficult.
Yeah,
Like I can't really I can't really select a particular tree. So I might have to
yeah.
take maybe another street then, because it's difficult
It's
to point
okay.
out a single tree. Mhm.
It's reality. You can see
Mm.
from the branches if a tree. I think they are oak trees, no?
Uh,
If they grow like
Probably.
that,
Mhm.
it means that they are in stress. If
Oh,
they
they're in
create
stress.
a lot
Mhm.
of these branches, yes, they are in stress.
Okay. They have not been
Maybe
trimmed.
because
Mm.
yeah, the street. Yeah, maybe they don't have enough space below ground to grow.
Okay. Yeah. Yeah, but
Or
then
what's also
that's what, like,
possible,
I think
the
when I'm cropping the images, when I'm selecting these
yeah,
images, I think it might
hmm
it might
yeah,
give me different results, because it's not um like when I take a square here, like when I take multiple squares
hmm
here to identify the trees, I think it will be a problem. I might get the wrong results, maybe. That's what I'm thinking.
yeah. Mm.
That is one
It's good that
challenge.
that's the purpose of if you
Mhm.
take this option to encounter
Mhm.
such real life
Mhm.
problems, because that's what AI modelers are dealing with many
Okay.
times. The labeling of the data is something crucial because
Okay.
if you make errors here, your result will also contain errors, but you have to make assumptions.
Yeah.
And I
Yeah.
think here, yeah, maybe in the front there, that one tree it's good, it's visible, the tree next to it as well, and then when this gray car
Yeah.
starts there, it becomes a bit
Yeah.
messy.
Yeah.
So yeah.
But again, I've taken a image that is closer so that the trees are visible. But then again,
hmm
yeah, it might be a bit difficult to identify.
yeah, yes, and the trees in the end of the street, they are too far away.
Yeah, I've taken those trees as well.
Mm.
But maybe
Good.
I've added.
Yeah,
Yeah,
because
that
this
will be
is your
good.
training.
Yeah. Oh, okay, maybe they're in another folder then. But yeah, I've taken those trees as well at the end of the street. So
hmm
one end to the other end. So that is what I've done
yeah,
from
I
this
think,
starting point to the end of the street.
yeah, I would in your training data set,
Mm-hmm.
because now there are maybe three, four images of the same trees or of the same street with the same
Yeah.
row of trees. I would
Mm-hmm.
maybe take one or two and replace the others, maybe the ones which were a bit fuzzy
Mm-hmm.
by other examples, because
Okay.
I think since it's very present, those trees, and the fact that they are in stress and contain these leaves on the down
Yeah.
on the stem. I
Mm-hmm.
would replace it by also some, but probably you have them in your training data. If you can show some other pictures.
So this, wait a minute,
Um,
this is how many images
same
exactly?
tree.
This is 10 items. Actually, I might have taken more because I think it was 20 images in total. And
Mm-hmm.
okay, there are five images for
Yeah, yeah.
validation as well, and then
Yes.
10 images for the training. Yeah.
Okay, okay. And there are already some other. Yeah, yeah.
Yeah, there are other
Okay.
varieties as well. Yes.
Yeah. hmm Okay, yeah. I would replace some of these pictures, which are coming now, of the same row of
Mm-hmm.
trees,
Mm-hmm.
by some more by other examples of trees. And you could add one of those. Maybe you could switch it with one from the validation, and you can see what
Ah,
your model will do
mm,
with such things. Probably
yeah.
it will try to recognize it because there are some of these pictures of this same street in your training, so it should be trained,
Yes. Okay.
and you can see the results. Here,
Mm,
don't spend a lot of time on really get a model which is 100% accurate and precise, because you cannot do it. It's
yeah.
impossible.
Yeah.
If you look at this, you already feel that those will be issues with the model. So
Yes.
the objective of this assignment is also to get familiar to these kind of models, because I think they are very powerful. Um, but you
Mm,
don't need to be an expert in getting this yeah, fully operational. It will be operational, but it
mm-hmm.
might not be 100% correct, because yeah, in science we can rarely be 100% correct. We always have
Yeah.
to make assumptions and work with uncertainty.
Uh, so
And
so
and
then
what was the
yeah.
error of your
Mhm.
code?
Error. There was no error exactly, but so if I open the tutorial here,
Mm-hmm.
so I got to the stage where I think this was I think it was make sense when I opened make sense in my browser, and then
Yes.
I let me see where it is. Yeah, so when I was in this part of the coding part exactly, so
Yes.
they wanted me to export the note file, the notepad file, into an IDML file, if I'm not wrong. It was somewhere here. Yeah, YAML file. Yeah, this one.
Yes. Mm-hmm.
So
Yeah.
that I couldn't do.
Yeah.
I think after that point I
Uh,
sort of hit a roadblock. I
yeah.
think I
It's
if I do this, I think it'll work. Yeah.
Yeah. Okay, that's good
This
because that's just replacing it. You can just type it.
Yes.
So if you created this first as a text file, it's car data
Yes.
dot
Hmm.
txt. You can just
Yeah.
replace it manually. This dot txt by dot YAML.
Yeah. Yeah. Exactly. Yeah, I will do that. And I
Yeah.
think after that, more or less, the tutorial is going fine. After that, I think
Hmm.
I'll see how it goes. But yeah,
Yeah.
that's more or less about this assignment. Um, so in a sense, so this part actually just gives us the number of trees. So
Yes.
this
Hmm.
resolves the part one of our assignment two, right? The part one, which is
Hmm.
the visible trees, and then
Yes.
this part one has nothing to do with our part two, which is the canopy cover, and part three, which is the distance to the nearest park, I'm assuming.
Yes. Hmm.
Yep.
Yeah. Those are different types of analysis.
Yes.
Um, what I
Okay.
what I can do. Uh,
Hmm.
um, So also for the other students who are in this session, do you have particular questions about this first part on the visible trees, or do you have other questions about the second part or the third part, or do you have any question at all? Because I gave a session last week to the students of Ghent also online on their request. And they said, well, we just want to be in this session to be a bit inspired by other questions. Is that the same for you? Or do you have particular questions in mind?
I think their mic is off. I don't know.
I think Juan, you just unmuted,
Yeah.
so you can speak, I guess. Or if your microphone is not working, you can type questions in the chat as well.
Oh, hi.
Hello.
Can I? Yes, hi. I want to have a question about the assignment 3.
Mm-hmm.
I don't clearly understand what should I do and what kind of things I need to submit. So
Mm-hmm.
there are separated two parts. So the first
Mm-hmm.
part is the essay on benefits of 3D.
Mm-hmm.
So it's kind of like uh, it's one A4
Yeah.
pages, and explains about these questions. And
Mm-hmm.
then
Yeah.
the part three is a different age for, I don't know. Yeah, so sorry, I can't understand the. eh,
No. So about this assignment three, it's indeed the first part is a reflection. It's an essay as it's called there. It's just you can write some things on the added value of the third dimension in the type of analysis we did. So in the demonstrations we dealt with geodata. In the first assignment you solved, we also worked with geodata, but it was mainly limited to two-dimensional data. So, for example, the demonstration of the aqueduct we worked with flat data sets, 2D. We didn't take the third dimension into account. For the first assignment, the La Palma lava flow, we also worked with rasters. So this octophoto, you georeferenced it to get an ID, and then you delineated the lava flow. I can imagine that such analysis, the main ID of the analysis, would benefit from having three-dimensional data available. For example, if you would know where the volcano would be, how high it is, where the valleys are. So it's in this assignment, it's a bit your reflection on how the third dimensional data, such as a digital elevation model, would help you to solve it. How could you have improved your results? So
Okay.
that's the first part, and
So
the second part is
yeah, okay. So in the part where is so compared to the benefit for the 2D models, and then if I use a 3D model,
Yes.
what kind of benefit for it about like
Yeah.
that?
Mhm.
Okay, then yes, part two is
And part two is try to work with these data again. So in the first session, if you remember it, we gave a demonstration on the 3D map view in QGIS. Wait, I can probably share my screen. So in QGIS, in this, I think the demonstration is also online. It's on Toledo. Wait, I can try to go there myself. So it's here. Session 2, 3D GIS. Sorry, it was session 2. It was this tutorial we followed to get such a result. Do you remember this?
Yeah.
And what you can see here is that this is still, or the OpenStreetMap in this case, is still depicted on a flat landscape. So here the question, or the second part of this third assignment, is to try to incorporate the 3D, the terrain as well. And it's fairly easy. So if you go to your 3D map view, you will see like this. Okay, in this case, I still have the greenery map depicted. So I have no houses, for example, no buildings. So this is still all flat. But what I also have is my digital surface model. I can show you in a minute how I downloaded this. And in the settings or the options, you can configure, and you see that there is an option called terrain. So in this exercise, you will need to use this option, terrain, and instead of working with the flat terrain, which is a default value, you can add a digital elevation model. Let's take the one I have now. So I have a digital surface model. I can use it, and yeah, I think I can increase the vertical scale a bit to exaggerate. Okay, I exaggerated a lot, but you can see that in this type of analysis you can. So here there are some hills. I'm in the neighborhood of Ghent, by the way. So you can use this terrain option to also visualize the third dimension of your terrain. So you can depict the houses which you downloaded, for example, the ones of the demonstration in the beginning, to visualize them on the terrain itself. So it's not flat, as you can see here. Okay, it's exaggerated a lot. Maybe it will also be a bit better to view if I change the colors. Okay, yeah, you cannot see my full screen, so I just adapted the symbology. Okay. So you see that you can express them also according to not diffusing out. There are even in the neighborhood of Kent some real mountains. If you exaggerate it. So that's the second part. Try to work with this to also include terrain as one of the underlying well to visualize this third dimension as well. So it's a fairly short assignment, because I know that the second one is a bit larger or heavier, more challenging, let's say. This is another assignment which can be done in maybe one day. Is a reflection, and then try to do this and depict the houses on top of it. And
Okay. Yes. Thank you.
yes.
Sorry, I'm like struggling with my audio. I didn't see this short demonstration, but last week I searched for the demonstration that you did in class of 3D,
Mm-hmm.
and I didn't found it in Toledo. Is it there?
I was also just looking for it, but it doesn't seems to be there. I can try to look at the because I recorded it. It was an on-screen recording, so I will look at it. It was basically this tutorial. So if you
Yeah, I
follow this
remember
tutorial,
yeah, I remember the class, but I don't remember very well the process. So I searched for the demonstration and I didn't found it.
yeah, I will check if I have it, and whether I can upload it under this topic again. And it's to solve this second part, you will have to go until here in the tutorial at this 3D map view, but then add the additional part where you can yeah. So if you go to options, configure, to also depict the terrain and not make it flat, as you can see here, would work with a digital elevation model, which you can download yourself and try to play with it. You can also add shadows, for example. It can be nice. But I will look at it. Yeah.
Thank you.
Professor, so when we switch on the terrain, will the buildings also sort of follow the terrain, or will they remain flat?
Yes.
Like, will they remain at one elevation?
Mm-hmm. No, they should follow the terrain.
Okay.
Yeah. But of course, if you exaggerate it a lot like this, I'm not sure if it will work. But
Okay.
yeah, because you see here, it's 10 times. It looks like in the south of France or something.
Okay.
The reason why I also had these data sets open was to give some more tips to solve this second assignment. Is it also something which can interest you?
Yes.
And I can also record this session. So what I'm about to do is give a short demonstration on how to tackle these three criteria of the second assignment and where to find the right tools, but also the right data sets. And so know that this part is being recorded. You can always, if you see the collaborate tab on your on Toledo, rewatch this recording. Yeah, so if you are stuck somewhere, to prepare myself, I already added the necessary data sets. So I added a digital elevation model, and the greenery map. This is my location where I can untick it. I found these data sets on Geopunt. So it's the data for Flanders. I was looking at the neighborhood of Ghent. But as you can also see in the description of the assignment, the map I used, or one of the data sets I used, was the Groenkaart, Vlaanderen 2021. So it's updated every 3 years. The latest version, which is available, is from 2021. And I think if you have selected your study site in Brussels, it might be more difficult to use this dataset, because you can see that Brussels is clipped, is being removed. But maybe on the GeoPortal of Brussels, you can find a similar dataset. There was one student who was working in the Netherlands, and if you go to the National GeoPortal of the Netherlands, they have a similar map. So there are different maps available. You can also look at, for example, ESA world cover maps. That can also be a valid data source. So if you are not working in Flanders, this might be, it's a global land cover product based on Sentinel data sets, 10 by 10 meter resolution. Okay, the one we have here, the greenery map or the Groenkaart, is 1 by 1 meter resolution. But of course, we cannot promise that kind of detail if you work with global data sets. So this 10 by 10 is still okay if you want to use it. So the first thing I did was download this data set, the greenery map of Flanders 2021. What you can see on this data set, let's go to Leuven, for example. There are 4 classes in this data set. You can see the yellow color, that's agriculture. Let's try to check. Yeah, so indeed it's in Dutch, it's landbouw, so it's agriculture. The gray obviously is gray infrastructure, so it's called all the rest, I think, and not green. The dark green, this is called hooggroen, which means high green. It's vegetation which is higher than 3 meters, so you can assume that these are trees. And so if we look at the 30% criterion, we can check, well, tree cover will be those pixels which are classified as high green. And there's also another one, the light green, that's low green. So vegetation lower than 3 meters, but also not agriculture. So there are these 4 classes, which means that if you zoom, so you can see that, for example, in the around the campus, or here in Arenberg Castle, there is some grass. Okay, that's not completely there are some grasses, but there are also some roads next to it, some open grasslands here as well, some forests in the park. If you go up to the this side of the Celestijnlaan, there is also some agriculture. So you can see that this map, it's something we can use in this type of analysis, especially for this 30% criterion. And another data set which I also downloaded, it's the digital surface model. So if you look at Geopunt at DSM, you can see there are 2 options. So maybe I can try to translate this to English. Let's see what's, yeah. So it's also using the right terminology. That's great. So you have this digital surface model, but also a digital terrain model. Do you know the difference between a digital surface model and a digital terrain model? This is, for example, a good representation of the difference. The digital terrain model gives you a raster data set of your ground level. So it will depict this brown line here. The digital surface model will give you the height of the object itself. And if we want to look at the first criterion, this tree criterion, and check the number of trees which are visible from a certain point. For example, if I'm standing here as an observer, this tree will be blocking my view, and I will not see all the trees which are behind this tree. For a tree, it's maybe a bit difficult to depict, but imagine this was a building. I cannot see behind this building. So this is blocking my view shed. So if you want to work with the AI model or the computer vision model, as you were presenting first, that's fine. The view shed, that's the alternative. And then you will need to use this digital surface model as an input, because you will need to know this height of the objects, because everything what is behind this building, for example, I cannot see it.
Yeah.
So that's why on Geopunt I looked for this digital surface model. And that's what I downloaded. You can see here, for example, the trees are present, the buildings are present in this data set. And so the value which I'm seeing here, for example, this pixel value of 55.6 meters, it's representing the height of this building above the main sea level. Okay, so I download these two datasets. If you just you can do this by clicking on the three dots, going to the information, and then you will see the download service. I can switch to English again.
So, Professor, digital elevation model and digital surface model is the same, right?
Yeah, it depends a bit on the terminology, because a digital elevation model, it can be a digital surface model or a digital terrain model.
Okay.
But there are also others who use the term digital terrain model to use this as the umbrella term of both a DSM and a DEM.
Okay.
So it will. That's a bit fuzzy, this terminology. But in this case, on Geopunt, it's called the digital surface model, or DSM, and the DTM. It's the terrain model, or the yeah. So you need to have this. Here you see digital elevation model founders. That's the general term of also the underlying data, and here we are looking at DSM, digital surface model. And if you read the description, it will tell you that that's the dataset you need: a digital surface model of the ground level, including objects in a raster format with a resolution of 1 by 1 meter. So if you go to this dataset, you can click on download, and you can, if you work in Leuven, for example, use tile number 32 and download the data. I downloaded this already in advance to be able to show it to you. So you see here, this is my digital surface model, and this is my greenery map of the region around Ghent. Okay.
Yeah.
Just imported in QGIS. I also added the OpenStreetMap, for example, as a background layer with Quick Web Services plugin. If you want to tackle this first criterion, you will need to specify your location. In this case, where did I put my location? Let's start again. So I can just remove this and show you how to start from it from scratch. Do you know a nice place in the city of Ghent? For example, I have no idea where I am. I imagine I am living in this building here, number 75. So this is my location of interest. You can make a new, so the first thing, so again, to frame it a bit better, I will first start with the first criterion, this tree. So I'm living here, imagine, in the Bouw de Losstraat number 75, and I want to check if there are 3 trees visible from my house. You can do it as your colleague showed earlier with Google Street View imagery, train a computer vision model in order to detect trees. what we can also do is make use of information on the height of this location and its surroundings to compute or generate a view shed, meaning within this view shed, everything is visible. So the first thing you have to do is create your observer point, so your location. You can create a new point by clicking here on this new shapefile layer. You can specify the location and your map. Let's call it Boudelot Stad 75. Okay, it's a point data set. I will work with Lambert 72, and that's it. So now I created an empty shapefile. This is similar to what you did in the first assignment when you were working or delineating the lava flow. You also started with an empty shapefile and you filled it with these polygons depicting lava. So if you created this data set, you can edit it. You can start adding points like this. And so it's telling me. By the way, did you see when I was creating this shapefile, or was it on my other screen? Yeah. So I just noticed now this window popped up on my other screen. So I did it. I clicked on this layer. You filled in these panels. You saved the location where you are storing it. Specified that it's a point. That's what I did. 72, and then I hit OK already. And so that's just what I did. But I just realized now that it was depicted on my other screen, and you can only see this screen. But okay, then I added this point. I can click on save, and voila. I have my observer point. And so this is my location. The next thing you will have to do is work with this plugin called Visibility Analysis. This will by default not appear in your processing toolbox. It's a plugin you will have to install. You can do that by clicking on Manage and Install Plugins. Voila. And you look for Visibility Analysis. And you see that this visibility analysis calculates visible surface from a given observer point over a digital elevation model. And that's something we want to use. Before, these types of analysis just worked with a buffer, maybe 500 meters around the house, counted the number of trees which were present in this buffer, and said, okay, from this house you can see maybe 20 trees. But that's not accurate, because as we've seen before, buildings can block trees. So it's, especially in this urbanized context of Ghent, it's very difficult to work with these fixed buffers. So we need to run these kind of visibility analysis. If you installed this plugin, you don't have to do it right away. You can just follow along and try to do it yourself. You can always watch the recording afterwards. First thing you have to do is create viewpoints. It just means that you are preparing your data set according to the same format, the format which your next analysis can read. You have your observer location, so it's my point data set. The digital elevation model I'm using here is my digital surface model. You can specify the observer height. So if I'm standing, this is a default value. The eye height is typically 1.6 meters, and the radius of analysis in meters, it will check for all the pixels in a radius around 5 kilometers around this building, whether it's visible or not. I will already decrease this value in order to speed up the process. You can leave the default value of 5,000. Just in order to speed it up, I will make this radius a bit smaller, because in the city of Ghent, I will never see further than 1 kilometer. I hit run, and you see that I have a second point data set. So it's my point, which I had already, but now there are just some differences in the attribute table. These parameters, which I just defined, are specified in the attribute table, and that's it. And so it's just preparing your data set in order to be able to be processed in the next step. And the next step is analysis. You can compute view sheds, as you can see here. There are different types of analysis, binary view shed, depth below horizon, or your horizon itself. We will opt for binary view sheds because this will depict whether a pixel is visible or not visible. The horizon, for example, can also be interesting. It can delineate the outer edges of a view shed. Imagine you are standing on top of a tower, and you want to specify, well, if I construct a new tower, how far will the horizon be? So you can depict this, or you can visualize it as a polygon. You can also work backwards in these type of analysis. Imagine you want to construct a new windmill in the neighborhood of the surroundings of a city. You can also check how many houses, how many buildings will be able to view this windmill or not. How many people's view will be disturbed by this windmill. Or if IMEC decides to build a new tower, for example, you can see, well, okay, this new tower will be visible from the Arenberg Castle, for example, or the view of the Arenberg Castle will be disturbed by this new tower in the back. So it's these types of analysis. You can also solve them with this view shed or with this visibility analysis. You specify your observer location. That's the dataset we just created. The digital elevation model is again my DSM. And you can leave it as it is and click on Run. And now this algorithm is computing per pixel. Is it visible or not? Is it maybe blocked by a house or by another object or not? So you can see here, let's put my location on top of it again. You can see I have a binary dataset. That's what we specified with zeros and ones. And 1 means that it's visible, a 0 means that it's not visible. If you untick this box, you can see that this row of buildings, it's blocking my view already. So you see that this everything what is behind my buildings, it's not visible. So that's already clear. And then here, I can see things, but there are also maybe some trees on this side. I can maybe change the transparency a bit. And so there are also some features probably here. There are some trees according to this digital surface model which are blocking my view. And so that's something that's already something we have to pay attention for, right? Because if this is a tree and there is a clear trunk, maybe the crown only starts at let's say 8 or 10 meters, I will be able to see through the part below the trunk, below the crown, where only the trunk is. In this type of analysis, the view is supposed to block, or the crown is supposed to block everything, which is not true, of course. But what you can do after that is use this data set. For example, I'm adding the Google Street View imagery. Here is what you can see. So there is a tree. It's not present on the OpenStreetMap. So let's check. No, on the OpenStreetMap, there is no tree. But if you look at the Google satellite imagery, here is a tree, and this tree is probably blocking my view further away. You can also check Google Street View and try to check it yourself. What you can see here is, for example, if you make this type of analysis, this is probably also a tree. You can also add the groenkaart, so the greenery map. And indeed, this is a tree, this is a tree, and this is a tree. So in this case, according to this analysis, I can see 1, 2, 3. Well, it's hard. You also have to make assumptions here to check if this is only one tree, or maybe it's more than one tree. So this is a second tree. This is also visible because there are some pixels with the value of 1 in my view shed. So I can see 1, 2, 3, 4 trees. And also here, I can also see a 5th and a 6th tree. So according to this analysis, I can see 6, oh no, here, a 7th tree in my view shed. So that's here in this case, it would be the value of 7. You can, if you want to make this, now we just counted it, so I can make a separate file. So visible trees, for example. I can also make it a point data set Belgium Lambert. Voila. And I can start edit it and start adding points. So for example, for every tree I count, so this is a tree, up I can make a point, this is a tree, this is a tree, this is a tree. Here these trees are not visible. Here this tree is visible. This tree is visible. And you can always, if you're unsure, add some additional layers to give you some more clues. So in this case, I've now put a point. Oh, I didn't do it. No. Here, for example, I'm not sure if this would be a tree because on the greenery map it's depicted as low green. So here I can okay, and here is the other tree. Yes, here I think this is also a tree. But you see that the greenery map is from 2021, so there's also an assumption we are making. And so maybe in the last 3 years, this tree has grown until a value higher than 3 meters, and now it's appearing as a tree on my in my analysis. So if you counted all the trees in this way, you can check how many trees you have in my attribute table. So I have a total of 8 trees which are visible from my location. So that's a way, or that's an approach to solve this first part, the tree criterion. As an alternative to the computer vision model or the YOLO model, you can also do. Are there questions about this?
So in this map, the view shed that you have created with the 0 and the binary view shed that you created, so it signifies that from the point that you have marked. So I'm trying to visually understand what does the white actually mean. Like, is it saying that from the orange point, that is what we are able to see? So everything that is white is everything that we can see, and everything that is black is basically blocking our view, correct?
Yes, exactly.
Okay.
Yeah. So if this was the street, for example, let's use the street map again. So the street, yeah, it's this is visible. So it's open. So I can check it. Here there's water. It's also nice. So here I can watch this this part. I can see over the water, but the water itself I cannot see because it's lower.
Yeah.
I cannot see downwards because I will be able to see the other side of the river, but not the water itself. So also here, until it hits this this building, and my view is blocked totally.
So what it is trying to do exactly is it's trying to radiate these lines from a singular point and see where it hits. Is that how it's sort of doing?
Yeah. Okay. That's a view shed. There is a nice tutorial landscape archaeology, where they did this to check in the island of Naxos in Greece how far these buildings could view, which part of the islands could be viewed by this set of, I don't know how many, 15 or even more towers. So these people used to build these towers all over the island. And you can see that a number of areas were visible from more than one tower. And the island of Naxos, there are some mountains blocking your view, so it's also nice in this setting.
Okay.
And they also did the backward analysis where you could see or also test the visibility of the towers. So from a certain location, how many towers could you see? Because in the past, these might have had very important functions, where, for example, in terms of communication with other towers. So you can also check if you have to construct a new tower in order to optimize your communication strategy in a time without phones.
Okay.
What you can also do is, if you have the data set, go to the IMEC tower, put your point on top of the IMEC tower, and check the horizon around this tower, or do the inverse analysis, and from which points in the city of Leuven can you see the IMEC tower, and when can't you see it? But this is just to tell you that's the alternative. That's the less, in my opinion, less challenging alternative to the computer vision model. But you are, of course, also invited to test this option as well, as you did. The 30% criterion, then you need this groenkaart or greenery map. So I can then take these results of the first analysis. I need my greenery map, and what I want to do now is check the amount of pixels of high green. So in this case, my dark green color, which has the value of 1. Count the amount of pixels in a neighborhood around my point. If you want to, I think in the assignment description, I suggested 1 kilometer around my house,
Yes.
for example.
Yeah.
So if you want to create this neighborhood of 1,000 meters around this point, do you remember which analysis it is that you have to use?
The buffer.
Yes. Okay. Yeah, so here is my house. And so indeed, you can compute a buffer around this location. It's 1,000 meters. That's it's mainly the city center of Kempten. And what I want to do now is, within this buffer, let's adapt the symbology. Within this buffer, count the amount of pixels of high green. So the first thing I will have to do is filter out these pixels of high green. That's on my tree cover. Do you remember how to do this? How to filter in a raster dataset?
The raster calculator. Yeah.
Yes, you said it in Symfony. So a raster calculator, and it's from my greenery map, so the groenkaart, and it had the value of 1, as you can see when we identified this. So where this is equal to 1.
Yeah.
I think I did this already. Okay, I didn't. So I will call this, it's the high green, just hold on. So now it's checking for every pixel which pixels are have the value of high green. These will be getting the value of 1, and all the other pixels get the value of 0. As you can see, this is also a binary raster data set. Okay, since I am now working with only ones and zeros, this can simplify my analysis. Because what I want to do is count the number of ones within this buffer. And what's additionally interesting here is the resolution of this map. So also the high green map has a resolution of 1 by 1 meter. So 1 pixel in this map also represents 1 square meter. So if I know the amount of pixels with this value of 1 within my buffer, I immediately have the total area of tree cover. Because if imagine there are 20 pixels, this corresponds to 20 square meters. You agree?
Yeah.
Okay, so if I would know the total of ones, so the total of high green pixels within this zone, and if I divide it by the total area of my buffer, I have my fraction, I have my ratio of tree cover, which I can check, is it larger than, equal to, or less than 30%? Already visually, you can see that it's less than 30%. And so the city center again will not meet this criteria, but still we want to compute the actual number. And that's something you can do with zonal statistics, is the name of this tool. You will find it under the processing toolbox under raster analysis. You will find it zonal statistics. Zonal statistics allows you to compute statistics from a raster layer within a polygon layer. So your input is the polygon, the buffered. And so you see this algorithm calculates statistics of a raster layer for each feature of an overlapping polygon vector layer. So I have my buffer, which is my region of interest. It's the neighborhood around my location of 1 kilometers. My raster is my high green, right? So my binary raster. And if you click on run, you will see it's creating a new polygon. And in this polygon, in the attribute table, I will find my statistics. So in total, now you have to pay attention. So in total, within this polygon, I have 3 million pixels. From these 3 billion pixels, I have 177,000 ones. Because the sum of all the zeros and ones is this value. So if it was tree cover, it had the value of 1. If it was agriculture or gray infrastructure or anything else, it had the value of 0. So if I just take the sum, I have my tree cover. Because I'm not interested in the zeros, only in the ones. So that's what's done when making the sum already from this binary raster. So in total, I have 177, 339 square meters of tree cover in a region of 3 million square meters. So the mean value, if you divide this sum by the count, is 0.057. So it means that 5.7% of my region was covered by trees. And so this means the fact that you can try to compute it yourself, try to check if it makes sense, but it does. In this case, the tree cover of 5.7% is being found. So it's definitely less than 30%. So that's something you can easily check by computing these zonal statistics. where for a region, for a raster layer, you can check the statistics from a given zone. In this case, 5.7%. So from my location, I was able to see 8 trees, which is good. It's better than this tree. But my tree cover is not 30%, but only 5.7%. So that's how you can solve this second part. So the 30% rule. Again, if you don't work with a greenery map, if you work with a different region, you can try to check for different data sets, like the ESA world cover, where you can also find information on trees or another data set. Okay, is this clear? Are there questions?
It's clear.
Clear, yeah. Thank you.
Okay. Yeah, I hope this will help you to solve it. What we can do next is this third criterion. It's the 300 meters from a park. Here we will need to have, this is close to exercise 19 of the tutorial, where you perform network analysis. So you also here in your processing toolbox, you will see this function network analysis, or this set of functions. For example, shortest path point to point. That's something we can check. So we have our point location, our house in the Bodelostraat 75, and the park. In order to run these analysis, you will see also from exercise 19, you will need a network. It's a network analysis. You will need your street network, but also your park, because we know the start point, it's our house, but where is my closest park? It's something we need to download as well. One of the tips we give in the assignment description is to use the OpenStreetMap and data from the OpenStreetMap. I think this was also part of the first demonstration where we looked at the Quick OSM plugin. Yeah. So if you don't have this plugin yet, manage and install plugins, look for Quick OSM, and this Quick OSM plugin, here is also a button to open it, will allow you to communicate with the server of the OpenStreetMap or with one of the servers and download the datasets that you are interested in. Let's look for the park dataset first. So if you look for park, you will see there are several features dealing with parks, RV parks, theme parks, dog parks, and so on. We are interested in land use and nature, or land use park dataset. Within the city of Ghent, or I can just use my canvas extent, since I zoomed out a little bit, I will look for all the parks which are present within this, this canvas extent. Okay, and I can click on Run Query, and it will download my parks. So you see that this is my set of parks. There is already, I selected a very nice point because, yeah, that makes sense. Where the trees were before, that's already a park. So in this case, my distance to park will be 0. But for the sake of the exercise, we can select a different park. We still need to download the street network. We can do that as well through the OpenStreetMap. So there is a feature on streets. There are many features dealing with streets. So also, for example, pedestrian streets, because this algorithm or this concept of Cecile Konijnendijk, it's a walking distance. So we can also make use of bicycle roads or pedestrian roads. So it's good to keep all these features in. Again, I will use it from my canvas extent and download my street network. This takes a bit longer. If you would have additional datasets or official datasets of your location, you are also free to use this. So in this case, maybe if you're working in Ghent and you already have a dataset from the municipality itself of the urban parks, you can use that dataset. So you're welcome to use it. So you see that I have my streets, so they are in orange. I have my parks. I can now run this analysis on the shortest path. Let's not, for example, let's try to look at the park which is situated a bit further away. Because in reality, I will have to do this. But since this is a park, you can already say, okay, my third criterion is 0. There are 0 meters between my house and my park. Okay, maybe 10 meters if you have to cross the street. But anyway, it will be closer than 300 meters. Let's check, for example, the shortest path between my point and maybe this park, for example, which is a bit further away, just to check how the algorithm goes. Shortest path. You can select your network. So here is the highway, motorway link. So the network we downloaded from the OpenStreetMap. I will look at the shortest path. If you need to work with, for example, speed limits, you can also check for the fastest path, because in the OpenStreetMap or in another official data source, you will also have information about the maximum allowed speed. For example, some roads you can only drive 50 kilometers an hour, other on a highway 120 kilometers an hour. So there can be a difference between the two. But in the reasoning of Cecile Konijndijk, it's only the shortest path that will count. So my start point, I can click on the map. I can go to my house and select this as a start point. My endpoint, I can select a park. I didn't know which one I opted. Let's try for this, for example. Here again, you will see that we have to make an assumption, because I don't know where the entrance of the park is. This is not given in OpenStreetMap, so I will only assume that, for example, here. Let's assume there is the entrance. So I clicked on my endpoint over there, and I have it stored. Et voila. You can specify if you're, for example, working with a car data set, or that you can only use a certain direction, or that there is an attribute in your data set or in your attribute table telling you whether it's one direction or not. And you can click on run. And what the algorithm is doing now is computing the shortest path. Let's make it a bit more visible. So I have to remove this buffer. Yes. So between my starting point and my endpoint, based on the streets which I added from the OpenStreetMap, this route is the shortest path between point A and point B. And the length of this path, you can find it in the attribute table. There is a field called cost, which is giving me the distance in meters. So in this case, to go from my hometown to this park, it will cost me 1,335 meters distance. So imagine this was the only park nearby, it would fail the criteria. So we would not have an urban park in a distance less than 300 meters. But of course, I just took this as another example, because in reality, this is less than 300 meters. So that's also something you can do and take the actual street network into account. Because here, what you could also do is, for example, I can create a buffer of 300 meters around my house and count the number of parks which are situated within this buffer, but that's not the actual distance. For example, for this park, maybe this falls within a buffer of 300 meters, but I'm not a bird. I cannot fly in a straight line. I need to take the route there. So maybe if you have to take this bridge, it would be larger than 300 meters. And so it's just better to use this street network in these types of analysis and not work with fixed buffers. And so that's the third criterion. So in this case, I've now solved the assignment in not solve it, because you will still have to write a report and discuss your findings. Also discuss, what I would be happy to read is discuss how these types of analysis and these findings can help you as urban planners. And it's also something I would like to read. But you see that the technical part of this assignment, if you opt for this one with the view sheds, if you opt for the computer vision model, it might take a bit longer. but it's doable in also a limited amount of time if you already have the right data sets, of course. But in this case, to solve this for this part of Ghent, I only downloaded the DSM, so the digital surface model, and the greenery map, and the rest, so the street network and the park network, I downloaded this from the OpenStreetMap within QGIS. Yeah, so this, if you would have these two data sets, download them from Geopunt, you have a point, well, if you're working in Flanders, and all the rest is something you can access directly within QGIS. Are there questions about this third criterion, the 300, or other questions related to this second assignment? No questions yet. So note that this is also recorded. I can stop the recording if there are no more questions. You can always watch it and try to, well, if you're stuck somewhere. Okay, are there other questions about this course or about the other assignments or other comments?
No, not really. But yeah, it's pretty interesting that I mean, all of these methods are pretty interesting for us. I think they will be quite useful for our assignments further in the course. In fact, most of this proximity analysis and buffer analysis is quite useful for us, I think, as urban planners, and I think they might be used in government sort of schemes as well, which I was not aware of at least. So that's pretty interesting. Yeah.
Yeah, I think this algorithm to compute view sheds it recently won a prize. I think there was a session of Flagis, and they gave prizes to the public, and I think one of the studies working with view sheds was won this prize. I think it was also related to this 300 criterion. Here you see I just found another random paper. What can we see from the road? Applications of a cumulative view shed analysis on a US state highway network. It's also something you can check also to take into account in more landscape planning exercises.
Yeah.
Okay, are there no other questions about this second assignment or about the third assignment?
It is about assignment, but about the skill test, if it's possible, I want to know the answers and how to solve the problem.
Okay, yeah. I can show you, yes. Yeah, but before that, maybe are there other questions about assignment 2 and 3?
No, just if to remind if you can upload the tutorial.
Yes.
Because I missed the other part because the audio was not working. So
yeah, the tutorial of the
3D.
for the third assignment, the 3D map viewer.
Yeah.
Yeah.
Thank you.
Okay, I can do that after the session. So I will also take the skill test. But I will first stop the recording because that's you can use this recording to look at the second assignment. So the skill test. Yes, skill test. Yeah. Okay. So it was looking for for the effect of planting new trees for climate adaptation in the surroundings of Leuven. So there were some data sets I gave you, the buildings downloaded from the GRB. Yes, it's mentioned here. So the same what we used in this demonstration on 3D map view. Potential tree locations. So a shapefile representing the point locations of potential tree planting sites in the study area. If you would pay attention to this dataset, you would see that I downloaded this from the roundabouts of the city of Leuven. So I just downloaded the roundabouts, and I suppose that on every roundabout you should be able to plant a big tree, because it should be fairly easy to do this. You will not have that many limitations when you don't have to remove parking lots, for example, or front yards. It's just a roundabout. That was something I tried to simulate. The heat stress map, a raster layer representing the expected number of heat wave days, also true data. So I obtained this from the VMM geoportal. So it's an existing data set from our Flemish government. And DTM, so a raster layer representing the elevation in the study area, also from Geopunt. So I didn't invent any of these data sets myself. I just looked for what's available and tried to make an interesting exercise out of it. How many heat wave days are expected at the location of the building with unique ID? With this unique ID, well, let's look at it. So, yeah, I don't need to save this. So let's import these. How did I do this? Was it this? Yeah. Yes, so I can do the. Here I have. Okay. Look at the OpenStreetMap still in the other window. And then my DTM and my heat stress. Yes. Voila. So the first question was how many heat wave days are expected at the location of the building with unique ID, with this unique ID. How did you solve it? Do you remember this?
This one was from the attribute table. You filter by expression, if I'm not wrong.
Yeah. Yeah. So you could indeed look at the fields and values in the description itself. UIDN. It's this value. So I look at where this is equal to this value. Select features, and there should be one feature. We can zoom to the selection, and this is my building. And now I was looking at the number of heat wave days, and let's change the symbology here. Now I'll make it unique values from reds. Voilà. Now, where is my building? It's situated within this pixel. So what you could do is simply click on identify. Is it opening in a different box? I think I just closed my identifier. Okay. No features. Sorry, I have to tick this layer. Yes. So it's 29. So in this building, the number of expected heat waves is 29. Okay. So it's just making the selection and then identify this, and it's 29. How many potential tree locations are situated within the center zone? You have your list of potential tree locations. If you look at the attribute table, you'll see there is information on the zone. So it's again this filter by expression. Fields and value where zone is equal to center. We can select the features, and we have 6 potential tree locations present in the center. Still okay? Those were 2 fairly basic questions, right?
Yes.
The next one, what is the surface area in square kilometers with the number of expected heat wave days higher or equal to 25? How did you solve this?
Raster calculator again.
Mm-hmm.
This is the third question, the surface area?
Yes. Yeah. Yeah.
Oh yeah.
So heat
Yeah,
stress
raster
is
calculator.
larger than or equal to 25.
Yeah.
I will just I will not store this result. I will put it on the desktop. Okay. 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 So what I'm doing now is indeed with the raster calculator again make this binary raster with ones and zeros. One where it's higher than or equal to, and 0 if it's lower than. Okay. How did you compute the surface area?
Polygonize.
Mm-hmm. And it's raster conversion polygonize. Raster to vector, so indeed this heat stress 25.
So even though we did this conversion, it can be done without the conversion as well, right? Like we can, if we know the pixel size and
yes.
yeah.
Yeah. Yes, indeed. Because here you see in the properties, 1 pixel is 1 by 1 meter. Yeah. Yeah. Okay. Okay. Yeah. I think when working with the raster calculator, I made it 1 by 1 meter because originally this data set of heat stress is not 1 by 1 meter.
Yeah, it's larger.
100 by 100.
Yeah.
So indeed, that's why. Yeah. So if you think here, you can compute probably with the histogram already. But that's. I think if you look for this this type of raster layer statistics maybe from heat stress 25 is statistics. There are several options also for the other questions. So if you use the different approach, polygonize, that's something we did in the tutorial as well. So that makes sense. Here, for example, the sum is again equal to this area because we have zeros and ones and the sum of all the ones. And I again have a resolution of 1 by 1 meter. So let's check here. So 2, 6, 6, 8, 4, 3, 7, 9 square meters. So in square kilometers, this is 26.68 square kilometers. When I have now vectorized this or polygonized, I open my attribute table. I can compute the area. So with field calculator, I can create a new field area. I can click on OK, and I have my total area of everything. And now again, there are other options. So what you can do is dissolve recompute area and get it, or use this sub field where I'm looking at this vectorized map. The sum I want from my area, but I want to add an expression. I want to filter only those which had the value of 1. So dn is equal to 1. So only my areas with okay, so my dn is equal to 1. And I have my sum. No, wait. I want the sum of the area. Okay, I cannot add this expression. No. I thought I could also add a filter in this sum. I have to do it solve this in a different way. So from my vectorized, let's first take this. I can now in this field select my ones, select features. Yes, and now I want my statistics of my selection only.
I think that the tab is not showing fully. I think the statistics tab. Yeah, it's at the bottom, but it's not showing that.
Yeah, I remember that it indeed was. Oh, maybe if I switch indeed. Yeah, if I would go to my other screen, I think it's because I'm also sharing this. Yeah, so there should be this option of selection. what I can do is
Or you can drag it out. The statistics tab, you can drag it out.
maybe I can put this one below. Oh, yeah, my statistics. Yeah, that's okay. Now everything is gone. Oh, yeah, okay. Yeah. Yeah, selected. Come on. Selected features only. And I have the same results. So this 2.66, well, 26.68 square kilometers is also appearing here. And so there are several options. You could have used the raster layer statistics, then you shouldn't have factorized this, or work with this sum that would also have done it. Okay. The fourth question. So if a tree can have a cooling effect on all households in a range of 100 meters around it, how many buildings can fully or partly benefit from planting a tree on all suitable locations? How did you deal with this?
A buffer.
Yes.
An intersection between the new layer and buildings.
Yeah. So this buffer of let's say 100 meters around the trees. Huh? I don't like this layout anymore, but okay. So buffer, you have your potential tree locations, a distance of 100 meters. And voila. And then you computed the intersect of the buildings and the buffer, right?
Yeah.
Yeah. So I have my buffered, my buildings. And the result, let's check it visually, are indeed my buildings, which are situated around my my trees. And the amount of buildings, you can check it in the attribute table, 2,142 buildings would benefit from it. Okay, so that's indeed this combination of a buffer and that was too quick, because you see here what I forgot to tick, this dissolve option box. Did you get the same results, or
No, we dissolved it, and the
Yeah,
result is
no. 1,824.
yeah, I got
Yeah.
1,800. Yeah, around that.
Indeed, that's because you had to dissolve it. So potential tree, I was a bit too quick, sorry. 100 and dissolve result. And then you see this is one polygon, because in my guess with or my first estimate 2000, I counted these houses double because they were influenced by two trees, and that's not how reality looks. So I have my buildings, my buffered. And now my intersection 1,805. Okay, So that's the fourth question. Also okay for you, Juan? Because I see that you have your microphone on.
Yeah. It's okay. I had few more, but I think it's because of the precision of the buffer.
Yeah, it's possible. That's possible. Yeah.
Yeah.
How many potential planting locations are located on a slope steeper than 2 degrees? Because it might be a bit more difficult on those locations to make this planting hole. There might be some risks of erosion in the early phase. So let's check. How many planting locations are located on a slope steeper than 2 degrees? How did you solve this? This was the most challenging. That's also why this was the last question, because here you would have to be a bit more inventive. First thing you did was probably compute the slope.
Yeah.
Okay, and what did you do next?
After that, at least for me, I use the raster calculator to create a new raster with slope that is greater than 2 degrees, and that I polygonized polygonized
Yes.
that layer. But
Yeah.
because it was such a huge raster image,
Yes.
I clipped the raster extent only to the tree's shape file.
Yes.
And
That's good.
yeah, and then the vector intersection still took a lot of time. So at least for me, I manually counted the trees because it
Okay.
took
Okay.
a lot of time.
Yeah. Yes. That was also the challenge and a bit of a trigger to be creative. The fact that you this DTM this slope has a resolution of 1 meter as well. So it's
Yeah.
really a gigantic data set. So indeed, the first steps create a slope. I think that's something everybody did. The raster calculator where the slope. So strange things happening to my screen. Okay. So slope is, what did I say? Larger than? Yeah, steeper than. Yeah. 2 degrees. Yes. Okay, so slope 2. And indeed, one option was to vectorizing this data set takes a lot of time, really a long time. So one option was to decrease the amount of raster, let's say, to vectorize because it's a lot. So you could do this. You already had this buffered operation around each of the tree planting locations. So in order to check how many planting locations are situated, you could first let's do this. See, it already takes a lot of time to load this raster. So you could extract, or maybe first, is there someone who did it in a different way? No?
No, I did it also through Polygonize, but it didn't work.
Yeah.
It didn't finish.
Yeah. But then, if you would have written out the steps you could follow, it would still be okay. Use this slope 2. You can mask this buffered. Voila, and you would only have this, this, and you could polygonize this in a quicker way. So this clipped. And then you would have made the intersect probably. So that's one way. And did the intersect and got, well, let's finish this. So you have your intersect between the vectorized have two vectorized, of course. Let's remove the one I'm not needing anymore. So I have my potential tree locations. I will look at the vectorized. Yeah. And this intersection result gives me my list of 40 trees, and I'm now interested in the amount of ones. So these, if there is a 1 in the attribute table, it means that uh, my tree is located on a slope larger than 2 degrees. So there are 13 trees. You could have counted this manually, but of course, it's always nice if you can automate this.
Yeah.
What is also another option, where if you would have had time, you know the concept, because what you want to do is you have a raster data set, slope 2 with my ones and zeros. You have your point locations, and you just want to know the value of your raster for a point. You could have looked for a function to find this. Let's this function called. It's only from this. It's extract from this. Function sample raster values. It's another option. So the vectorized worked, but if you would have tried to look for a function where you can extract the values of a raster for a point dataset, you would have found this sample raster values function. I know there was at least one student who found this. So this algorithm creates a new vector layer with the same attributes of the input layer and the raster values corresponding on the point location. So sample raster values, your input was your potential tree, your raster layer was your result of your raster calculator. If you then hit on run, it's very quick. So it's already ran, and you see you have your point data set and this result of your raster. And if you would afterwards run the same, so where your sample result is equal to 1, you would see that you would again have 13 trees meeting this criterion. So that was the quickest option. I admit you would need some time to look for the right function. The one with vectorized was a bit challenging. We had to think about a creative way to deal with it. But this was an alternative, and there might be other alternatives as well, which can still let you get some points for it or earn some grades for it. So even if you weren't able to, if you didn't think about masking a part of your raster, but you wrote that you would vectorize this afterwards, did the intersect and look for the expression and filter it, it's still okay. So yeah, I can still give you points for this. But that's one of the solutions for this skill test. Okay, was this clarifying for you?
Yeah, thank you so much.
Yes, thank you.
What did you think of the skill test? I thought it was also nice to give you some more experienced type of analysis, because this climate adaptation is also something you will have to deal with as urban planners.
Yeah, I think it was perfect, at least for what we've learned in this course. I think it was like a perfect amount of skill sort of evaluation. Yeah. And it's a real life scenario as well, so I think it helped.
Yeah. Okay. So, other questions? What we can do is you can I gave this demonstration to solve the second assignment test also for the people who arrived a bit later or who want to do this because I understood this also a busy period for you with your studios. You can always watch a recording. And I can you can keep on working with it now, so I can remain available for questions. Or if you're stuck later on, you can always drop me an email, and I can try to respond. Yeah, so it's up to you to decide. You can stay in this collaborate to work on it, and if you have questions, you can just call me back. I will be here. I will be step by. Or if you have other things to do, you can also work on those other things.
Okay, thank you so much.
Yep.
Yeah, thank you, Prof.
Okay.
Bye.
Yeah, bye.
Bye.